Okay, so here we go, lesson 4, gravitation. So gravity is something that we've looked at before. We started with gravity being equal to your mass times the acceleration due to gravity here on Earth. But gravity doesn't just exist on our planet. Gravity exists everywhere. And so we have this concept called universal gravity. And we've said that gravity is a force that exists between Earth and masses on its surface. If, actually, I should say in fact. In fact, gravity is universal. It exists between any two masses in the universe. So it's not just our planet and things on it. You got gravity acting between the Earth and the Moon. You got gravity acting between the Sun and everything that orbits the Sun. Our Moon, our planet, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto, and all of their moons, comets, and stuff. So there's no reason why gravity would be limited to just these things. Just because they're really big, that means their gravitational effect is noticeable. But as you get smaller, just because it's not as noticeable doesn't mean it's not present. And so there's got to be some sort of relationship between an object and every other object. You, your dog, the things sitting on your desk are all interacting with each other, even really minutely, gravitationally. So the diagram below shows two masses. We have big M and little m. Big M is the greater mass. It's capitalized. Clearly it's bigger. We want to compare the gravity forces on the two masses. Well, we have said things like, well, this thing has a larger mass, so this one is going to have a larger G, which we said earlier was gravitational field strength. Gravitational field strength. But we've also said that due to Newton's laws, every action has an equal and opposite reaction. So this guy is going to have a gravitational force backwards, this guy's going to be pulling this guy in. There's an Fg here, but if he's pulling this way with Fg, this guy's going to have to be pulling this way with Fg, and these two are going to have to be equal. The forces are exerted have to be the same because every action, even at a distance, every action has an equal and opposite reaction. So there have been a bunch of physicists over time that have experimented on gravity and universal gravitation and trying to figure out what these things are. One of them was a guy named Henry Cavendish. He was one of the first, but others since him have designed all sorts of ingenious experiments to measure this small force of attraction between two masses, regardless of their size. What was found was that the force varied directly with each mass. So they said that the force of gravity was proportional to the two masses, M and M, and was it says here, and varied inversely with the square of their center-to-center distances. What that means is the force of gravity is proportional to the inverse square. So that means 1 over r squared, where r is the distance from the center of one object to the center of another object. So the force of gravity is proportional to the two masses and is proportional to the distance between them. There is a constant of proportionality that we've measured. Basically, things can be proportional to something. What that means is they're equal to something up until some multiple. And what we've discovered is that multiple is this guy right here, big G. And we've discovered that this is constant everywhere in the universe. By looking at stars really far away and how they interact with the planets around them, or looking at objects on our planet and how they react with each other in a very minute way, we've seen that all over our universe there is this gravitational constant that seems to govern the force of gravity, which is really cool. So the formula that they derived for universal gravitation is this. Fg equals this big G, this constant of proportionality, 6.6 times 10 to the negative 11, times M1, M2, sometimes that's big M and little m, but I call it M1 and M2, divided by r squared. And so this is true for any two objects. This center to center distance is r, and then these two objects are going to have a force of gravity on each other. And it's going to be equal. So we're going to flip the page here. So you want to calculate the force between two 1 kilogram masses separated by 1 meter. And this is one of the ways that this universal gravitational constant was derived. But we're kind of going at it the other way. So here, basically how this works, this is super simple. We've got the force of gravity equals G M1 M2 over r squared, and we just plug in these values. G, which is experimentally verified, is 6.67 times 10 to the negative 11. 1 kilogram mass, and 1 meter between them. We find that the force of gravity between two 1 kilogram masses is this. It's very small, 6.67 times 10 to the negative 11 newtons. Almost not measurable. Well, not measurable by any of the stuff that we have at school. I'm going to show you in a sec how this compares to what we've been looking at for FG here in a second. Before we get there, though, we're going to see this thing here. We want to see what happens to gravity as things change. So we have two equal masses, m and m, and they're separated by some distance d. And we want to look at what happens when we make some of these changes. So starting here, F equals Gm1 m2 over r squared. Let's take a look at A. What happens when we double the distance? Well, if we double the distance, we're going to get F equals Gm1. I should have just called that m. Mm over 2d, and we're going to square that. I'm just going to bring that squared in, and we've done stuff like this before. I'm going to square it, and so what we're going to get is G mm over 4d squared. And so what this tells us is that the force of gravity, this piece here, is just what we started with for Fg. So this is just going to be equal to F over a quarter. So when we double the distance, we quarter the force. We have 1/4 the force of gravity. I'm going to skip B because we can see what happens here. We would cube it, and we would get the force is a ninth. We'd follow the exact same thing here. C is exactly the same. If I quadruple the distance, it's going to be 1/16 the force of gravity. Some of these other ones here should be pretty obvious too. If I double the mass, if I put a 2m here and leave everything else the same, it's just going to be 2 times whatever my force of gravity was. So this guy here is going to be 2 times F. This guy down here is going to be 4 times F. What happens if I have the distance between them, though? I mean, this is kind of an interesting one here. If which we'll look at, we'll look at it. So if we do F here, I've got F equals G mm over d over 2 in brackets squared. If I take a look at what happens here, I square this fraction at the bottom, I'm going to get G mm over d squared over 4. Now when I divide by a fraction, I multiply by the reciprocal, so what we're going to get here is G mm times 4 over d squared. So if I have the distance, what I've got is 4 times the force as well. It's 4 times bigger. And if we double the masses and the distance, what we're going to see here, so we doubled the masses, and if we double the distance, we can see that these 4's here are going to cancel out. So by doubling the masses and doubling the distance, this is actually going to stay the same. We have to double both masses, though. So gravity is usually really, really small. We can see that 6.67 times 10 to the negative 11 is a very small number. Unless one of the masses is sufficiently large. As you start to ramp up your mass in kilograms, gravity starts to become really, really noticeable. A planet, star, even a moon. The moon isn't that big, all things considered. But it's big enough to have a pretty substantial gravitational effect. So we're going to take a look here at example 4. We're going to assume that the mass of Earth is 5.98 times 10 to the 24. That's basically it. We rounded a little bit, but and its radius is this. That is true. We want to find the force that Earth exerts on a 50 kilogram person on the surface. We can basically ignore the size of the object, like you on the surface, because the Earth is 6 million meters radius, and you're like 1 meter tall. So we can ignore that one extra little meter because it really doesn't add anything to our calculation. So if we use universal gravity, we're going to get, look at G, M, little m, over r squared, and now let's plug in these values. G is 6.67 times 10 to the negative 11. The big M is 5.98 times 10 to the 24. Little m, u, are 50 kilos. And then the radius of our planet is 6.380 times 10 to the 6. If you run that through your calculator, what you're going to see, and we have to square the radius. Now, when you do the calculation, just to verify it, but the number I got is 489.95 newtons. Now let's take a look at what we would have done before. We would have said Fg equals mg. M is 50. We've said that G is 9.8. 50 times 9.8 is 490. So this approximation of G being 9.8 is good to within 5/100ths of a newton, which is pretty awesome. I mean, there are always more decimals that we could use here. Some of you may have looked at this in Physics 11, and the value uses 9.81, which makes it more accurate. But what we can see here is that this part of the expression, the universal constant of gravity, big M, the Earth's mass, and r squared, the radius of our planet, gives us that little g. You can see that when we run this through, and I'm going to do that right now, 6.67 times 10 to the negative 11 times the mass of our planet, 5.98 times 10 to the 24, divided by 6.380 times 10 to the 6 squared. If we run that, we're going to get a very familiar value. 6.67 times 10 to the negative 11, 5.98 times 10 to the 24, divided by 6.38 times 10 to the 6, all squared. And we get 9.79908, which we round to 9.80. Oh, I'm sorry, I'm dropping a little low. Which is pretty cool. We get the value we expected to get using universal gravitation or using Fg equals mg. We get exactly the same thing. So until now, we've been aware of 2 ways to determine the gravity field of a planet. The first way was the gravity field at a point can be determined by measuring the weight of a small test mass, m, and then the ratio of the weight in newtons to the mass in kilograms gives us the gravity field. So we have this. Effectively what we're doing is this. Fg equals mg. This is the weight of an object. Is equal to the mass times gravitational field strength. So what they would do, what this is trying to say, is on the surface of our planet, effectively weight would equal mass, is the idea. So they would take an object of a known mass, and then they would fly it to a particular point above the Earth, and then they'd weigh it. And we could see that, so then the ratio here, gravitational field strength would equal the weight divided by the mass. We could see that ratio, and so as we get further and further away, we would see that the gravitational field strength is actually shrinking. The gravity field can also be determined by measuring the free fall acceleration at a particular location. This is generally how we do it in high school. This is a lab that we, I don't know, I said something before that was totally bogus, the weight equaling the mass here at the surface. That's crap. I don't know why I said that. That's not true. We know the relationship between the weight and the mass at a surface. And that gives us a gravitational field strength of 9.8 here at the surface. So we know what the mass is. And then as we take this up here, we can know what the weight is, and then the relationship between them, or their ratio, gives us G, and as you get further and further away, we can see that G decreases. This is down here is a lab that we often do in Physics 11. I don't know if you guys had a chance to. When I've taught Physics 11, this is one that I do. It actually used to be in the Science 10 curriculum. The gravity field can also be measured by measuring the free fall acceleration at a particular location, because we've already established that F net equals ma, and so mg equals ma, and so g equals the acceleration. So we can figure out what the gravitational field strength is by looking at the acceleration of an object at a particular location. So that's pretty cool. Comparing these things, we get a result that I already showed you on the previous page, that little g, the acceleration due, or the gravitational field strength, is equal to big G times the mass of the object that you're around divided by r squared. So we can actually start to look at the gravitational field strength, not just at the surface of an object, but anywhere around an object. We just have to take r to be whatever the distance is from the center of our object to some point out in space, and we can start to do gravitational field strength calculations around an object somewhere in the universe, which is pretty cool. This last property is useful because what it has allowed us to do in the past is provide us with a means to calculate the mass of our planet. And we do that this way. The radius of our Earth can be measured using geometry of the sun's rays. They figured this out, I think it was like 4000 BC. I could be wrong about that. It might be a little bit more recent, but it was like thousands of years ago. Greek mathematicians had a pretty good measurement for the radius of our planet. So using this measure, we've measured it a whole lot more accurately since then, but with satellites and lasers and all sorts of fun stuff. But we're going to use this value, and we're going to use the fact that we know the free fall acceleration near the surface of our planet is 9.8 meters per second squared. We're going to figure out the mass of our planet. So we know that little g is equal to big G times the mass of our planet divided by r squared. We have established experimentally that the free fall acceleration for an object around our planet and close to our planet is 9.8 meters per second squared. So little g is 9.8. The universal gravitational constant is 6.67 times 10 to the negative 11. We know we're looking for the mass of our planet. We know the radius of our planet is 6.380 times 10 to the 6 meters. And don't forget to square it. That is a mistake that is very common to make. R must be squared. So solving for m here, we're going to multiply this up, we're going to divide this down, and so we're going to get 9.8 times 6.380 times 10 to the 6 squared divided by the universal gravitational constant of 6.67 times 10 to the negative 11. If you run that through, we're going to get a mass of 5.98 times 10 to the 24 kilos, which is pretty cool. So let's do a slightly more complicated question. We're going to put a 30,000 kilogram satellite into orbit, and we want to figure out what the net force of gravity is on this object. And so we've got gravity now from the Earth and from the Sun. We know where in the orbit it is. It's 45 degrees off center. And we want to figure out what the universal gravity is here. So what we need to do is force of gravity, well, forces are vectors, and so vectors are going to have directions, and we're going to add them together like we would any force. So here we go. First, what we got to do is we've got to figure out, so first of all, 200,000 kilometers, and we need that in meters. So we're going to have 200,000, and then we add 3 more zeros to put that thing into meters. So that's that distance there. And then this distance here is 150 million. So we're going to add 6 zeros. Kilometers, we're going to add 3 more zeros to put that into meters. So there should be 9, 10 zeros there. Good. We've got the mass of the Earth, we've got the mass of the Sun. So let's do it. The first thing we need to do is we need to figure out what Fg is. So there's some notation here. We're going to call this Fg Earth. We're going to start adding what the force of gravity is caused by down here. And so we've got G, mass of the Earth, the mass of the satellite, divided by the distance between them, or between their centers rather. So we're going to have 6.67 times 10 to the negative 11. Mass of Earth is 5.98 times 10 to the 24. We're told already that the mass of the satellite was 30,000 kilos. Big satellite. And we're going to divide that by the distances between them, which we already said was 200 million meters. Don't forget to square that. And we're going to see that the force of gravity on that satellite is actually a really small, relatively small number, 299.15 newtons. You can verify my calculation if you like. With these huge numbers, we may have expected this number to be a lot bigger, but this is actually a really small number, so this thing and we're dividing by a pretty big number down here. So we get almost 300 newtons, and so let's take a look at the force of gravity from the Sun. The calculation is the same, except our values are different. So 6.67 times 10 to the negative 11. Now I want the mass of the Sun is 1.98 times 10 to the 30. That 30,000 is still there. And we're going to divide that. Now the distance between them is huge. It's going to be 150,000,000,000,000,000. What is that? That's a million. It's 150 billion meters. That's quite the distance. And we're going to figure out that the force of gravity on that satellite from the Sun is actually 176.1 newtons. Again, maybe that's bigger than we expected. They're really far apart, but the Sun has a significant measurable force of gravity on an object orbiting our planet, which is pretty cool and has a whole lot of implications there. So now what we're going to do is we're going to figure out what the net force is, and we're going to figure out the net force by adding vectors. So we know that the force of gravity is going this way towards the center of our planet, and that's going to be 299.15 newtons. And this guy has a force of gravity this way. I just made it bigger I shouldn't have made it bigger. I should have made it smaller because it is smaller, but just to kind of exaggerate it here, 176.1 newtons, which means that this guy, when I add these two together, is going to end up going that way somewhere. So if we wanted to, there's two ways we could add this together. We could break this guy up into components and add the two, so like the horizontal component here would add to the 176, and then we'd have the vertical component. We could do it that way, or we could add these things together using sine law and cosine law. So I'll show you what those both look like. I'm just going to go down here to the empty space that I have. So if I wanted to use a sine law, cosine law, I'd look at this. I've got my 299.15 newtons. And I've got my 176.1 newtons. So when I'm adding, again, remember, we're adding tip to tail. This guy here is going to be my F net. So we know, I'm just going to add a little bit of green in here. We know that this angle here is 45, that big green one, which means this angle here would be 45, which means this big angle here is going to be 180 minus 45, which is going to be 135. So now I can use cosine law using these two and that angle to figure out what F net is. So I'm going to find F net is going to equal the square root of 176.1 squared plus 299.15 squared minus 2 times 299.15 times 176.1 times the cos of 135. So if I run this through, square root of 176.1 squared plus 299.15 squared minus 2 times 299.15 times 176.1 cos 135. We find that this is F net equals 441.6 newtons. And then we can figure out what the direction is using sine law. If you do use that, what you'll find here is that this angle, I'm not going to do the calculation, but this angle right here is 28.6 degrees, and I'm going to say above the horizontal, because north, south, east, and west don't make sense in space. So that's using sine and cosine law. I'll show you what it would have looked like to break these things up, and I'll do that up here. So if we break this thing up into components, what you're going to get is this guy here, the 299.15 gets broken up into an x component and a y component. And we can figure out what these numbers are. This is 45 degrees. Excuse me. That's 45 degrees. So this guy here is going to be 299.15 cos 45, which we find out to be 211.53. And this is going to be 299.15 sine 45, which is going to also be 211.53. What we're going to have to end up doing is we're going to add this guy to this guy. So we're going to get triangle looks like this. I had 211.53. This guy down here is the 211.53 plus 176.1 is 387.63. This is F net, and you use trig to find it, and you'll get the exact same values we had down at the bottom, 441.6 newtons at 28.6 degrees. But I'll let you finish that. That's pretty straightforward. So there's a lot here for gravitation. It's really quite cool. Not a lot of questions I'm going to give you for homework here. I want you guys to take a look at I want you to do 1. I want you to do 2. I want you to do I want you to try 5. 5 is a good question. I want you to look at 6. I want you to do Which other ones do I want you to do? Let's do 8 and 10. So that's the homework I want you to take a look at for this particular lesson. Good luck. As always, if you've got any comments, questions, concerns, feel free to email me.